Rules and randomness, and another look at Chebyshev. The group structures of the S model manifests a handedness due to Z6, and this is inherited by all future sets. All primes must now either be of the form 1 plus 6n, what we call left-handed, or 5 plus 6n, what we call right-handed. Also, all prime gaps must now evolve from various sequences of gaps which began their life as sequences of various lengths of 4-2 or 2-4. This is the fundamental building blocks, and from this everything is born. As well, we must never allow for the possibility of ever having had a 2-2 or a 4-4 in any subsequence. We can reduce this to a set of simple rules we call short-range rules, or SRRs. If the order of a set of gaps is even, then if its anchor prime is left-handed, then to the right is a right-handed gap, or it is right-handed, and to the right is a right-handed gap. Or, if the order of the set of gaps is odd, its anchor prime is either left-handed, and it has a left-handed neighbor to the right, or it is right-handed and has a right-handed neighbor to the right. There are some immediate consequences of the short-range rules. The obvious first one is that the gap of a gap of size 6n can pair with anything, while gaps of 2 plus 6n or 4 plus 6n must mismatch, unless of course it's with a gap of size 6n. For example, 8-6, 6-8, 8-4, and 4-8 are allowed, while 2-8, 8-2, 8-8, 4-10, 10-4, and 10-10 are banned. They will not exist in nature. If these were the only rules for tuples of arbitrary length, choosing a random sequence of length n has about a 1 2/3 chance of existing. However, this is not the case. There are an infinite number of long-range rules, which are not simple rules per se, but consequences of primal evolution. Each iteration of the S model provides the feedstock in terms of the gap patterns for future evolution, just as S2 gave us the SRRs. So looking at S3, we have the following gap sequences generated, and a trivial observation shows that while tuples of 6-6 and 6-6 are allowed, which means they can be produced by coalescing gaps, there is no way to produce a tuple of 4 6s in a row. Just simply not possible and will not exist in nature. The little we've been able to test is about half the sequences larger than triples that pass the short-range rules do not exist, though we've only been able to test through m equals 10. The set sizes are too big after that. Be that as it may, if this is the case, choosing a random sequence of length n has about a 1/2 times 2/3 to the n chance of existing. Induced topology. It seems there isn't a single branch of mathematics that does not provide some deep insight of the S model or the primes. Consider the following. Here we're using bold font to indicate the set plus all its residuals. That is, the larger set can be completely contained by the smaller set. All the members it generates are generated by the smaller set. Given a gap set M, we say the set of its ordered subsets is open for all the next gap sets and closed for all the previous gap sets. That is, earlier gap sets can cover most, but not all, of each next model, while future models can fully cover previous models. For example, the first step in constructing the next model is building the next prime copies of the current gap set, followed by consuming the first minor primordial pairs to create the first minor primordial new gaps. And these are not covered by older rules. What we are describing is self-similarity. That is, the S model can accurately describe almost one of the next set, and the degree of self-similarity becomes arbitrarily close to 100% as M becomes arbitrarily large. This is also recursive, such that given we understand everything up to some Sm, then some distance away k, with a little bit of algebra and other number theory, gives us this ratio of logs. Since humans will only describe the first handful of the S models, given the exponential growth of the sets, and k can grow arbitrarily large, realistically we're left with a portion of about 1 over the log of the prime of interest. Consider, for example, the prime equal 53 would challenge the world's largest compute center on Earth, while prime equal 61 would challenge the world's compute resources. Using 2000-bit primes for encryption should remain safe from prying eyes. There are simply too many primes and too many ways to hide semi-primes. Now we start a section we call the daemon. Given that we can exactly predict at least a count of twin gaps, we can ask what would happen at some m if instead of the composites being kicked out rationally, it went haywire and the members were kicked out were chosen at random. At some m, we have our second minor primordial set of twins from a collection of our first primordial set of gaps. We make our next prime's worth of copies and randomly choose our first primordial pairs of gaps to coalesce into new gaps. Twins can only be eaten and never born during coalescence, so the count in the next generation is expected to be as follows, where we're just doing simply random selection based on the length of the various subsets. And that gives us these final forms, which we're going to manipulate here, and we get to our next primordial, the second primordial, times some factor. Comparing this with the natural expected value, we get something roughly, once again, approximately close to 1, this time on the heavy side, a little bit greater than 1. That is, the S model approaches a uniform random behavior as m becomes arbitrarily large. That is profound. So, moving on. Now we'll look at Chebyshev's function and how to interpret it in the S model. Trivially, our next prime is equal to 1 plus the sum of the gaps. Let's replace the actual gap with the S model estimator, which is the logarithm of the prime. So that is, our next prime is equal to 1 plus the sum of the log of the primes. Large number approximation, we drop the 1, and that shows us we get Chebyshev's function. Looking at this again, trivially we begin our next prime squared is equal to 1 plus the sum of the difference of prime squares. Expanding the difference of squares and noticing that the gap, how we define our gap, so we can rewrite the entire thing in terms of only the gap and the prime. Replacing the local gap with the random operator once again, we get that our next prime squared is approximately equal to 1 plus twice the prime times the log of the prime plus some other term. We call this the B form of the Chebyshev function, which for large primes gives us that our next prime is the square root of the sum of the square root of twice the sum of all the primes times their logarithm. Experimentally, the B form is actually better behaved compared to the A form, though its properties still require a great deal more investigation. Together, the two forms tell us two different stories about prime number distributions. In the first model, every gap is unique and important in its own right, while the second tells us that the scale of prime squares, they lose some identity. We saw this before when we were looking at the averages of average tuple lengths. They're linear. Throughout these talks we've shown we can count substructures of the S model, and now we're going to look at this thing as a whole. The various gap counts at some particular iteration actually represent a local probability mass function, or PMF, which we call F of M, the local frequency density of each gap. Since the counts of a particular gap type in some iteration M, using our capital T notation, for some positive natural number J, the total counts of all gaps in the sets is our first minor primorial. We can naturally define the local frequency density as the type count at some iteration M for some J value, where J is half the gap, divided by our first minor primorial. That is, for some undetermined local maximum gap type, the sum from 1 to this max of 2J times the type count is our primorial. Or, dividing by our first minor primorial, we get the average gap is equal to twice basically the first moment of our frequency distribution. That is, half the average gap is the first moment of our frequency distribution. So we have this cool property set. The expectation of the set is 1, or the sum of the set is 1, while the first moment of the set is half the average gap. Very strange. Notice the dependency on half the log, the square root of our prime. This comes as a surprise that we can decompose a complex Euler product into a finite sequence. I mean, it's really strange. SM is the template from which the random future is being built, while the FM is the current gap spectral distribution. We also have a nice hint that the distribution of prime numbers is driven by the square root of x. We're going to come back to this later when we finish the Riemann.